Hello, everybody. My name is Zach Parrish. I'm the programming librarian here at the Bexley Public Library. Thank you all for coming out tonight. Just a quick note before we get started. This is a hybrid program, so we're happy that you all came out to the library to join us for tonight's talk, but we do have an audience at home over the live stream as well. So when we get to the end for questions, if you don't mind just raising your hand, that way I can come around with the microphone so that those at home can hear what mind-blowing questions you're all asking. And for those joining online, feel free to type any questions or comments into the chat at any time, and we will get those asked at the end. I also just want to give a big thanks to Wayne Schlingman and Dr. Stefan Frank for helping coordinate this series. We have been able to do this for a few years now here at the Bexley Library, so we're just really appreciative of Wayne and Stefan working with us. And we have one more of these, so we'll be back next Thursday, July 24th at 7:30 with another talk from OSU Astronomy Department. So we hope to see some familiar faces back. Tonight we are joined by Everett McArthur, who is a first-year graduate student working with Ji Wang, focusing on high-resolution spectroscopy of brown dwarfs, celestial objects that straddle the line between planets and stars. He is also deeply passionate about science communication, actively exploring how music, art, and planetariums can serve as creative mediums to share complex scientific ideas with the public. So please join me in welcoming Everett McArthur. Thank you.
Thank you for that great introduction, and I'm glad that you're able to shorten the very long bio. But nonetheless, so today I'm going to talk about things that you either have not heard of, have not seen, or will not see for who knows how long, possibly thousands of years. Although if you plan on living for thousands of years, please let me know. I would love to know, and I'm sure a lot of people also would love. But nonetheless, so today's talk is stellar flybys and where to find them. So if you're from the city, what this might be surprising, but these are stars, not planes or satellites. But this is something that you might see in a clear night sky, away from the city, away from city lights. And what you might see in the sky are the planets, for example. This is Saturn. You might also see Jupiter. And of course, if you are particularly well prepared as an astronomer exploring the outdoors, you might even see some constellations. But as the night goes on, these planets will move across the night sky. Each one will travel at various speeds and whatnot, and it might look different according to the nights, and their position might change, but nonetheless, the planets are moving as well as the moon. The sun, for example, also moves along the night sky, and, well, that is also why we don't see the sun at night. This is exactly why you have day, and this is why you have night. So, during this talk, we will explore what else is in motion and its effects on us, and how does it move? Why does it move? How do we calculate it? We will also be putting it all in perspective. So we are on Earth. We are in a solar system that orbits the Milky Way center, the galactic center. And what is our place as we move throughout the galaxy? And are we missing anything? Are there objects that we can't see? Are there things that exist in the galaxy that are simply too faint for us to be able to make observations and conclusions on their motion? So let's orient ourselves with our sun. It's fairly a typical star. The energy is provided via nuclear fusion, so atoms smashing together to create heavier and heavier elements. So you start off with hydrogen and keep going up to helium, and sometimes you might even hit iron and erupt in a massive explosion. And of course, we have the solar system. We have Mercury, Venus, Earth, Mars. This is the inner solar system, of course, so I'm not showing everything. And all of these orbit the sun, the central star. And so, of course, we have the asteroid belt as well. You have the inner solar system, and when you go farther and farther out, you then run into this belt of debris that was left over from the early solar system. So rocky materials, and if you follow the news or follow sci-fi articles or whatnot, sometimes what you might hear are these ideas of drilling into asteroids and extracting material. And indeed, asteroids have a lot of heavy elements. They have a lot of metals, like gold and iron, and these present unique opportunities to ask those questions. Whether or not we'll get there is something I will not talk about, but they are there. And so the asteroid belt is about 200,000 miles away from us, give or take. Or 200 million, excuse me, 200 million miles away. A small change. You won't be driving there, by the way, or taking a plane. But nonetheless, of course, you then have Jupiter, Saturn, Uranus, and Neptune. Jupiter being the largest of the planets and having 4 massive moons that we all know and love. So it has up to, I think, 63. I forget what the actual number is now. But these 4 moons are the largest of Jupiter's. So these are the Galilean satellites. Io being the closest, having massive volcanoes and everything. And even though it has a lot of volcanoes, believe it or not, Venus, which is the second planet from the sun, is actually the hottest planet in the solar system, reaching about 900 degrees Fahrenheit. So way hotter than anything that is in your oven at this point. And so you then have Saturn, you have Uranus, and you have Neptune being the farthest planet out. And for all intents and purposes, you might consider this the edge of the solar system. You have Neptune, and then you have the rest of the galaxy, and then that's it, and no one cares what else happens. But I am here to tell you that our solar system is actually far bigger than what we often think it is. And so you have the sun, and then you have Neptune, and by the way, this graph is not at all to scale. And then you have the Kuiper belt, which is this icy belt that exists between Neptune and what we call the Oort cloud. Now, the Oort cloud is a very interesting thing because it's a region of cometary debris. It's where we believe that comets originate from. And so what you might have heard is this object from outer space that is cruising through our solar system called 3I Atlas. And that is not from the Oort cloud, as far as I'm aware. But nonetheless, 3I Atlas, if it were a comet, it would likely come from the inner Oort cloud, or from the Oort cloud itself. And the Oort cloud is this massive belt that encompasses the entire solar system. And so, as you can see, Neptune out to the inner Oort radius, there's a lot of space there. And what we really understand to be true, what we really understand to be the outer reaches of the solar system, Neptune, that's only a fraction of the size of the solar system. It's about probably 1% of the solar system as a whole. But of course, the solar system is in a much larger galaxy called the Milky Way galaxy. And it moves throughout the galaxy. And of course, these are not real stars, if you can't tell. But nonetheless, it moves through the galaxy. It passes stars. And stars also pass us. And sometimes, one could pop up in our solar system. Not literally, of course. It'll just cruise in and say, how's it going, and then cruise out. But nonetheless, we call these stellar flybys. Stars that pass through our solar system, and they will exist there for a few thousand years, give or take, and then they'll cruise out. And this is just a result of our solar system moving and stars moving with it. And so the key questions that we're now going to answer is, how do you calculate the motion of the stars? Can you figure out the distance of closest approach? So at what point in time and at what distance will these stars be at their closest approach with respect to the sun? So the sun is the center, and then you have a star coming in, and you want to know at what point is it actually closest to the sun. And what are we missing? Because like I said before, there are objects that we might not be able to see. And so is there anything that we are missing as a result of that? So to start, we will first learn how to calculate the motion of the stars. And it begins with two things. Well, multiple things, but in this case, two things. Stars move with two components, the radial velocity and the transverse velocity. So what are these? Velocity is in the name, so something is moving. So the sun, for example, will move throughout the galaxy. And these two components, the transverse velocity and the radial velocity, are often used to dictate the position of the sun, to dictate how it moves throughout the galaxy. And so as I'm walking across a stage, I have a lot of transverse velocity, meaning that I'm moving perpendicular to you. I'm moving from left to right or right to left. Radial velocity, though, is something that you can't really see. It's purely a depth measurement. And so I'm moving towards you, and trying not to fall off, but you can't really tell whether I'm moving left or right. However, if I'm moving diagonal like this, then I'd have a radial velocity and a transverse velocity component. And so the key takeaway here is that the total velocity involves the transverse velocity and the radial velocity. And so if a star were moving through our solar system, it would likely have a very high radial velocity. And the reason for this is because as it moves through the galaxy, it has to pass through our solar system. It has to get from point A to point B, which is us. And so to do that, it needs to be headed directly towards you. So it's going to have a low transverse velocity and an incredibly high radial velocity. And so the Gaia telescope sends astronomers highly precise astrometric and photometric measurements of the stars. What do these mean? Astrometric meaning how the stars move, what's their position, what's their velocity, what's their radial component, what's their transverse component, and whatnot. And the photometry being colors, how bright is a star, how cool or how hot it is, and et cetera, et cetera. And so who bakes in this audience? Anyone bake here? Cakes? Yeah, there are a few hands. All right. So when you're baking, you need some ingredients, right? You need flour and I don't know, baking powder. You can tell I don't bake, so I'm trying here. I'm really trying. If you have any recipes, let me know. But nonetheless, like baking, you need ingredients. And so these ingredients in this case involve the parallax, photometric measurements, radial velocity, proper motion, and effective temperature, or just temperature in this case. Now, we aren't trying to bake anything. We're not trying to bake a cake or bake a star, although a star is definitely baking us in the summer. But nonetheless, what we are trying to craft is an understanding of where the stars are going to be at a certain point in time. And so we'll start with parallax. And so parallax is the apparent shift in the night sky. And this is purely a result of just different vantage points of where the Earth is in its orbit. And so what this looks like is the Earth is moving and the star is moving. The star isn't actually moving, it's just when we look at it from a different point of view, it looks like it's over there instead of being over there. And the best example of this, and I'm sorry to do with all of you, but hold your finger up. I see you laughing, yeah. Yes, so extend it out, arm's length, and then close one eye and close the other. And what you might see is your finger might move left and right. But move your finger a little bit closer and do the exact same thing. Do you see your finger shifting? Yeah, I see some head nods. And that exactly is parallax. The parallax is the apparent shift. It's not actually moving, it's just because you're looking at it from different points of view. And so we can use parallax as a way to understand distance, because as you saw, when your finger was farther away, it shifted less. But when it was closer, it shifted more. And so that tells you that there is a relationship between how far the star is and its parallax, or its apparent shift. And then, of course, we have photometric measurements, so how bright the star is. And then you have radial velocity. So like I said again, radial velocity is purely a depth measurement, something that you can't really see, but it's crucial to understanding how stars move, what their components of that movement are. And so to understand radial velocity, you need to use something called spectroscopy. And what spectroscopy is essentially the study of light to extract information, whether it could be elements or abundances, or to understand what is the composition of the sun or of other stars outside of our solar system. And so light emanating from the star will get dispersed through an instrument and broken into a rainbow. And this rainbow, or this array of colors, if you will, can then be mapped into a graph that shows the intensity versus the wavelength. Intensity being the y-axis and wavelength being the x-axis. And then these squiggles that you see are absorption lines. So these tell you what that star is absorbing, so to speak, or what energy is being lost in a very specific wavelength of light at a certain intensity. And so now the radial velocity here, this is where radial velocity comes in. Because if the star is moving, then there's a shift. There's a shift with the colors that you'd see from a certain instrument. And that shift allows you to understand how fast it's moving. There's a relationship between the shift that you see to the radial velocity. And another example of this is when astronomers study exoplanets. So exoplanets are planets that orbit other stars. And oftentimes what you might hear from NASA is, we discovered a new planet. You can't live on it because it's probably hellish and all kinds of bad things and burning and whatnot. But nonetheless, astronomers use a radial velocity method as a way to search for planets, because you're looking at the wobble of the star. So the big orange ball is the star moving around its center of mass. And then you have this blue ball moving around it, or blue circle, if you will, moving around it, and that's causing the star to wobble around. And this wobble can then be traced to a spectrum in the bottom right-hand corner. Left hand? Left hand. Right hand. Left hand? Left hand. Nonetheless, so listen, when you're on the stage and you're trying to figure out, all right, which way is the left from the vantage point of person, it's a lot of work. But nonetheless, so now you have proper motion. Proper motion is the apparent motion of the stars as the sun moves. So you have parallax and you have proper motion. Both have to do with stars moving somehow, some way, some will. But the proper motion is a direct result of just our sun moving through the galaxy. Or moving through the galaxy. And so While parallax is just the apparent motion, and just the apparent motion of the Earth moving and taking from different vantage points, the proper motion is something that's physical, something that is a result of the sun moving through the galaxy. And then, of course, you have temperature, which is just how hot it is. And I will tell you now that every single object that I will talk about, you cannot live on. So that being said, now that we have our ingredients, we can start baking or cooking up the time and distance. And so to derive the time and distance of closest approach for a star or a stellar flyby, you have to make an approximation. And the approximation is called a linear motion approximation. And what linear motion approximation is you're assuming exactly that's linear in motion. So it's moving in a straight line. Astronomers are not good at naming things, and I think this is probably the clearest name of them. But nonetheless, so as a star moves, you're assuming that it's a straight line. And the reason for this is because we only care about a very small wedge in the galaxy. The galaxy is huge, it's massive, and obviously as stars move through the galaxy, it's basically a circle, depending on who you talk to. But you don't really care about the circle. If you really look at a small point on a circle, then it'll just look like a straight line after a while. And so we're assuming that's going to be linear, and you're taking the total proper motion. So now you're looking at the proper motion, and you're taking that and making an analysis on how fast that star is moving or where it's moving. And then you take the transverse velocity, you take the radial velocity, and then you get the total velocity. Because remember, the total velocity has two components, the transverse velocity and the radial velocity. And then you have time and distance. So using these calculations, you can then use what we understand of Newtonian laws of physics and laws of how planets move and whatnot to then create a simulation to see how all this changes with time. And so in the video that's going to play, it'll take some time, but in the video that's going to play, you have the sun at the center, and then you have stars. All the white points are stars. And when you run these calculations, you see how they move. And this is real data, by the way. So every second in the simulation is probably a few thousand years. And what you'll notice are a few clusters moving through the screen. There's one right down there, and then there's another one up in the top right-hand corner. And this is all real data. And so now the question is, what is the effect of a stellar flyby? What force will it impart on the overall solar system? And so this depends on the mass of each object, so each stellar flyby, how fast the object is moving, so fast objects will have a low impulse, and the distance at which we approximate the impulse. And so a close-in object, a massive close-in object, is going to have a larger impulse than a farther out small object. And what impulse tells you is the overall force it's imparting in the solar system. So if a star pops in, what will it do? Will it fling a planet out of the solar system? Will it fling cometary debris and fragments into the inner solar system? This all depends on the impulse, basically how much force or what effect will it have on the solar system. And so putting all of this together, we can then create a graph to describe what flybys happened in the past and what flybys will happen in the future. And this depends on the radial velocity. Radial velocity being positive tells you that it's moving away from you. Radial velocity being negative tells you that it's moving towards you. And so positive radial velocity objects will be moving away, and that will tell you that it was probably either A, a stellar flyby in the past, or B, a stellar flyby or or it was never a stellar flyby at all. And so we have past on the left hand, we have future on the right hand, we have the present in the middle, and then you have distance. So close-in objects being at the bottom, you have far away objects at the top. And so now we can create a graph. So each of these objects are stars that we have calculated a distance of closest approach and a time of closest approach. And what you'll notice is this massive circle at the bottom of the plot, and this star is Gliese 710. And if you look it up, you'll find Death Star hurtling towards the solar system and all manner of dramatic articles and whatnot. And in fact, it has the largest impulse. So the circles that you see tells you what effect it will have on the solar system. And so Gliese 710 being the largest and the closest approach tells you that it's going to have a huge effect on the solar system. And by the way, this is a few thousand years. So, nonetheless, we can now put it in perspective. So, you have the sun, you have Neptune, this is the same graph again. You have the Kuiper belt, and then you have the inner Oort cloud, and of course there's the outer Oort cloud, and then once you leave the Oort cloud, then you hit the nearest star. But Gliese 710 is going to be situated almost exactly inside the Oort cloud, if not fairly in the inner Oort cloud or in the inner solar system, or I shouldn't say inner solar system, but just the inner radius of the Oort cloud. And so the question is, are we missing anything? So I talked about this, as the articles say, Death Star, but really just a star moving through the solar system, or moving through the galaxy as well. And even though it has a massive impulse, that doesn't actually mean it's going to do anything when it is there. So what this means is that the star will come in, it'll come through the Oort cloud, and it'll leave through the Oort cloud. But you're not actually going to see the effect immediately. It's not going to be, oh no, there's a star, oh no, there's a meteor, and now we're done. What's going to happen is the star will be there, and you'll see a resonant effect over time. So slowly but surely you'll see orbits change, slowly but surely you'll see things change over time. And this can take thousands, tens of thousands of years to actually see. So long story short, we're fine. Now, the question is, are we missing anything? And so you can create a plot showing hot to cold. And you'll notice that blue is hot, red is cold. And this is not a mistake at all, because the redder that you are, the cooler that you are. This is for stars. The hotter that you are, is the bluer that you are. It's a bit counterintuitive. And we can create a plot that also shows how dim or how bright a star is. And so dim being, red, and then bright being really yellow. And so we call this the color magnitude diagram. And what I'm showing every single point is a star from the Gaia telescope. And so the orange and red being where most of the stars lie. And the points that I'm showing are the stellar flybys, the top 10 stellar flybys. And so we call this line the main sequence. So this orange dashed line from the top of the plot down is called the main sequence. And what the main sequence is are stars that are still fusing hydrogen in their core. So stars start off fusing hydrogen. So remember how I said that the fuel source of the sun is nuclear fusion, smashing things together to create heavier and heavier elements. And so the main sequence are all of these stars that are still doing that. Now, to move off of the main sequence, though, you then have to fuse helium. And when our sun fuses helium, well, by then we should be off of the Earth, because it will get very hot. what's going to happen is the sun will require more energy, it'll require more force to create helium, and it'll expand. The outer atmosphere of the sun will expand, engulfing or getting fairly close to the Earth, and it'll keep moving up the periodic table. So helium, and then you'll see carbon, and nitrogen, oxygen, and so on and so forth. Now, it won't get up to iron, because to fuse iron, it requires a massive star, something incredibly hot, something big. And our sun is not that, and most stars are just fusing up to carbon and oxygen. But over time, it'll cool, and it'll lose the outer layers of its atmosphere. And what will be left is a white dwarf, an object so dense where a teaspoonful will fall right through the teaspoon and fall right through the Earth. And so our sun and Gliese 710 exist in those areas of the color magnitude diagram. So the question I'm going to pose to you is, do you think we're missing anything in this circle in the bottom right-hand corner? Do you? Yes, yes, you'd be right. You'd be absolutely right. So we have stars like our sun. They have a certain mass, they have a certain radius, they have a certain temperature. And then you have planets, like Jupiter. You have a gas giant planet with a certain radius, a certain temperature. And between stars and planets, you have a gray area. Brown dwarfs. And brown dwarfs are strange objects. And I recently learned that the difference between a planet and a brown dwarf is that I think one does not float. So, interesting fact for you. But nonetheless, so brown dwarfs straddle the line between stars and planets. And they challenge our understanding of how planets and stars form. So for example, planetary formation starts off with a protoplanetary disk, the birthplace of planets, and the lifetime for this disk is about 1 to 10 million years. And in this disk, you have astronomical dust, so 0.1 microns, a few millimeters. And over time, planetesimals will form. So these building blocks will then coalesce together, they'll grow, and you'll have planetesimals. And then you have protoplanets, embryos of planets, sizes about 1,000 kilometers or larger. And then, of course, you have giant planets. So the formation for this is, again, 1 to 10 million years. And you have rocky terrestrial planets. And so these in the early solar system are just moving hitherto and fro, crashing into one another, creating larger and larger planets. And then after a while, planet formation is complete, and the time scale is a few 100 million years. And so the question is, do brown dwarfs form the exact same way as stars, or do they form as planets? Or is it a little bit of both? This is a question that's still being actively researched. But what makes brown dwarfs more complicated is that the sun and Gliese 229a both have nuclear fusion in their core. So they're both fusing heavier and heavier elements. Jupiter does not have nuclear fusion, but it does have its own heat source, so to speak. And brown dwarfs, while they can't initiate nuclear fusion, they do, however, start off incredibly hot. So they start off incredibly hot, and they're not hot enough to start hydrogen fusion, but they are hot enough to fuse like an offshoot of hydrogen called deuterium. And over time, these brown dwarfs are going to start collapsing and getting heavier, and this is when they start getting a little bit cooler. They're losing heat because now they're condensing. And so brown dwarfs are at the far end of what we understand to be stellar. So we call them substellar. And so with stars, you have spectral types. You have OBA, O being the hottest of the stars, and then M being the coolest of the stars. But then for brown dwarfs, you have a separate spectral type, L, T, and Y. And sometimes M, that's a complicated thing, but sometimes. But nonetheless, brown dwarfs are this weird gray area that is still actively being studied, and these objects are incredibly faint. And so I pose to you, what are we missing? It's brown dwarfs. Brown dwarfs are a class of low-mass substellar objects that can't sustain hydrogen burning, and these are too faint for you to actually get accurate astrometric measurements. So Gaia, for example, has a limit. There's a certain limit that Gaia cannot measure a velocity for. And that limit is conveniently around the brown dwarf range. And so for all intents and purposes, we have this massive sample of stellar flybys, but then we don't know if there's anything else that we're missing because we don't have a radial velocity for brown dwarfs. And radial velocity is incredibly important because it tells you what direction that stellar flyby is moving. Is it head towards you? Is it moving a little bit towards the left? Or is it moving directly towards you? And this matters because M dwarfs, being the very, very far end, and remember how I said that brown dwarfs sometimes can get into the M dwarf range, they make up at least 76% of the mass function of our galaxy. And so that's a huge proportion that we're just conveniently missing because Gaia can't calculate a radial velocity. Now, Gaia is a powerful instrument. It sends highly precise measurements, but for the purposes of brown dwarfs, it's tough. And so we take the same plot, and the black points are the stellar flybys that we had from Gaia, and the x-axis being the time of closest approach, and then the y-axis being distance of closest approach. And with brown dwarfs, these are the red points on the graph, you now have two objects that might be considered stellar flybys. Oh, but they're not stellar because they're not stars, so we call them substellar flybys. And so what we have learned is that we can calculate the time of closest approach and distance, and there is a possibility that brown dwarfs can find their way in our solar system. Now, the plot that I showed earlier had this massive circle around Gliese 710. And with brown dwarfs, now that you have them in this plot, do they also have that massive circle? Do they also have a huge impulse or a huge effect on our solar system? And the answer is maybe, but not a huge circle. And the reason for that is because even though they're likely traveling fast, because they wouldn't be substellar flybys unless they were traveling fast with a high radial velocity, but their problem is their mass. Their mass is incredibly small. It's comparable to Jupiter. And so with a small mass but high velocity, it's not going to have a huge effect on our solar system, but if you have many of these passing by, almost every single million years, every 1,000 years or so, then eventually you then raise a question of, well, will this destabilize the solar system and what will happen over time? And people analyze this. The analysis there is difficult because then you're trying to understand orbits across a large period of time, but it does raise interesting questions. And so, will a shooting star kill us? Probably not in our lifetime. I think we're okay. Could the dinosaurs have been killed by a passing star? This is a question that is very fascinating, but it's incredibly hard to answer. Because the problem is that there's a resonant effect. I mentioned that when you have a stellar flyby, the star will, move around the solar system for a few thousand years or so and move out, but you're not actually going to see the effect immediately. You're not actually going to see everything just occur all at once. It'll take thousands of years more to see the orbits change, to see what's going to happen with time. And so if a person were to make this analysis, they have to take that into account. They have to see, okay, that stellar flyby could have come, and then they'd have to track it a few thousand years into the future and then understand, okay, what's the actual effect of this, and so on and so forth. And so there's a lot of variability, and that's what makes it difficult. However, in an era of big data in astronomy, and what I mean by big data is that we were in a time where you had these massive telescopes outputting incredible amounts of information. So you have the Dark Energy Spectroscopic Instrument, for example, or DESI, which tracks cosmic acceleration across time. This is a 5-year survey. And it has probably 5 million galaxy spectra. So it looks at the spectrum of galaxies, and this is for 5 million of them, and it's still going. And then you also have the Vera Rubin Observatory. This is an observatory that just opened a few weeks ago and just now started collecting data. And across the time of its observation, it'll likely output 6 petabytes of data. Do any of you know what a petabyte is? It's a lot. You have a terabyte, and then you have a petabyte at the end. And so we'll have a huge sample or a huge understanding of the motion of the stars, and perhaps our understanding will change. Will more brown dwarfs be encountered as substellar flybys? Will there be another object that just appeared out of nowhere that's even closer than Gliese 710? And all of this comes with more information, more data, and with time. And so, in conclusion, as a summary, we calculated the motion of the stars. Stars and brown dwarfs can pass through the solar system. And we can calculate with some amount of accuracy how close a star will come and at what point it will come. And with that, I open the floor to questions.
So while those in the room think on what they want to ask, we did have a few come through online. Someone asks, is the definition of our solar system the region of space in which the gravity of our star dominates?
Yeah, that's an excellent question. The gravity of our sun falls off very quickly as you go farther and farther out. And people often use the edge of our solar system as the point at which the solar wind encounters the radiation field of the galaxy. They call it the interstellar medium. And this often is used, and the boundary at which that encounter happens is called the heliopause, which is farther out than the Oort cloud. And so if you're just looking at the Oort cloud, then yeah, you can say like, all right, that's the end. And in fact, throughout the talk, I define that as like, that's the edge of the solar system. But the Oort cloud, people often argue that the heliopause is the actual edge, and the Oort cloud is the immediate area where the gravitational force of our sun might still dominate. Yeah.
There was another one. I'm going to try to see if I can get this right. Someone asks, on the graph of closest approach distance versus closest approach time, why were most of the data points at times near now?
Yeah, that is an excellent question. And a lot of it has to do with how complete we are. So what does completeness mean? It means, have we found all of the objects within a certain distance of the sun. And for Gaia, for example, Gaia is, I think, 90 or 99% complete in terms from 0 all the way out to farther out than our sun. However, as you go farther and farther out, then completeness falls off rapidly. And so really what we have then is, or what we're biased to, and I use this word very, very loosely, are the objects that are close in towards the sun, objects that have precise astrometric measurements, and objects that are known to have a high radial velocity.
So you had mentioned, I think it was that Gliese star. Sometime in the future, we'll be passing somewhere near the Oort cloud. What kind of effect is that going to have, assuming there is still life on Earth at that time? What kind of effect would that have on life on our planet, for example?
Yeah. So this is I don't want to give you false information, so I will say that this is this is a question I did not answer myself, and this is research that is ongoing at other places in the world. I looked at brown dwarfs specifically, but people have often asked the question, could a passing star give the Earth a healthy dose of radiation? And that involves looking at fossil records and looking at looking at various things that would tell you how much radiation was present at that time. Are there any abnormal spikes? And it's my understanding that that analysis is also hard. Unfortunately, everything that comes with understanding what effect a passing star could have in the past is difficult. Because there's just a lot of variability. You still have the sun, you still have the Earth going through whatever at certain points in time. And so it's difficult, but it is an interesting question. And I guess the short answer is who knows. But the long answer is that a passing star would dose the Earth in radiation, and that might be traceable.
Sorry if you mentioned this, but when you mentioned the radial and transverse velocity,
Yeah.
like, what is that relative to?
So this is relative to us.
Okay.
So if you are moving from left to right, then I'd say, oh, you have a high transverse velocity and a high radial velocity and whatnot.
Okay. Got it. Okay, cool.
Do brown dwarfs have any of their own planets or
Ooh.
moons?
Yeah. So brown dwarfs are difficult because they're faint, and that creates problems in addition to calculating their astrometric values. The reason for this is because oftentimes brown dwarfs are companions to other stars or other objects, and so you can have a binary system where you have two stars orbiting each other. And if you have an incredibly faint object next to an incredibly bright object, you can see the problems. However, then the question is, oh, well, is there a moon? Well, the object is already really faint, and the moon is already really faint. Now you have even more problems. However, there was an interesting research article published by Jackie Faraday's team at the Museum of Natural History that found effectively northern lights on a brown dwarf. They found aurora on the brown dwarf. Or I should say they found strong indicators, very strong indicators for aurora. And the question is, what's the source of that? So our understanding of Jupiter is that you have Io, which is the closest in moon to Jupiter, and Io has a lot of volcanoes. It has hundreds of volcanoes, in fact. And so Io injects charged particles into Jupiter's atmosphere, and this actually creates or helps create the aurora on Jupiter's northern poles. So similar to the Earth, how we have the northern lights are a result of the solar wind interacting with the Earth's magnetic field and getting funneled into the poles of the Earth, creating the northern lights and the southern lights. And so the brown dwarf, as I understand it, and I did not take part in the study at all, so this is really just me reiterating everything, is that it's an isolated object. So, now I'm not saying that there's a moon there, but I'm also not saying that there's a moon there. If there is no other star in the vicinity, and you have an aurora, then what could be causing it? Could be a moon. Perhaps a volcanically active moon. Perhaps a moon that would be the first time that we found a moon on a brown dwarf. Anyways, to answer your question.
Yes, I'm still trying to understand how we capture an image of these stellar flybys.
And I should say these are not images.
These are not images?
No.
What is this? With the data points that we're moving?
Yes, these are data points, and we're using the information from Gaia.
Okay.
Here we go. Yes, we're using the information from Gaia to then see how these points move across the night sky. So we did not take a picture from distant in space and take a picture of the sun and see how the stars move. What's happening is a sun was situated in the middle, and they looked at how stars move around the sun. So based off of our understanding of their astrometric values, they looked at how the stars are moving with time.
Okay.
And I should say that this was a simulation created by I believe also Jackie Faraday at the Museum of Natural History. And they looked at how these stars move with time. And so I should ask Jackie. I'll ask her.
So we see the effects of stellar flybys because of how the stars are moving around them. And
Yes.
Okay. And so we could see the effects of flybys that have been gone a long time ago because there'll still be an effect and things will still be moving even though that flyby is gone. Is that correct?
Yes. So we're able to make an analysis on the past stellar flybys and the future stellar flybys based off of their radial velocity. So based off of the radial velocity, their mass, and their distance, you can then create an approximation, so the area of the circle being how big of an impulse it'll have or how big of an effect it'll have. And you can then see, well, okay, based off of our calculations and based off of the radial velocity, you can see where it'll be or where it was in the past. And of course, there's an error around this, and I do not want to communicate that this is it. But you can see how these stars move with time. There's a great paper by Corin Baylor Jones, Corin being Coryn, Baylor being Bailer, sounds like a spelling bee, where they do this exact analysis and they investigate with more data and more information, what are we missing and what can they do based off of the analysis that they did. And so the brown dwarfs, for example, the brown dwarfs that were included were thrown into this mix and use the exact same calculations to see, well, are the brown dwarfs also going to have a similar effect? And that is when you arrive at, you can have a past stellar flyby and you can have a future stellar flyby.
Someone online asked, can a brown dwarf ever become a star or a planet under the right conditions?
Ooh, that's a great question. I do not think they can become a star. I say that with an asterisk. But so brown dwarfs are complicated. Everything about them is complicated. But this is why I love them, is that when you have a brown dwarf just formed, just new, it's incredibly hot, and it usually starts off as an M dwarf. So M dwarfs being on the very, very, very far end of the main sequence and being incredibly hot, these M dwarfs then condense and they start to cool with time. And so this is when you start getting to brown dwarf regime. The brown dwarf regime being very cool, and it's going to keep cooling. And so MLTY, these are the spectral types of brown dwarfs. Y is the coldest, but if you ask an exoplanet person, then there's some variability here, because you can have a brown dwarf planet, you can have a brown dwarf, and most people say that 13 Jupiter masses, so 13 times the mass of our Jupiter, is roughly the boundary between stars and stars and brown dwarfs, excuse me. Brown dwarfs then can sink below the 1 Jupiter mass limit, and then that can cause some problems. So long story short, what defines a brown dwarf and what defines a planet is something that is hairy.
Well, if anyone wants to stick around and ask Everett more questions, you're welcome to do so. Everett McArthur, thank you so much for this talk. It was very fascinating.
Yeah.